And well, first of all, being one of the organizers, since this is the closing talk of the half-year program, so I'd like to thank all of you for attending this program. And I think it turned out to be very successful. And I also would like to the real organizer David taking care of everything. And well, so I'm sorry for not talking about subfactors. but today I'm talking about something else, but it's related to Radha Henike's generalized mixed dualism, and so probably it's fit with the subject of the program. So this, before I forget, this is joint work with Hiroki Matui. So, I started with fundamental algebras, so still many people took fundamental algebras. So for a person like me, when I work on the sister algebras, then it's natural to bring a nice idea which was successful in fundamental algebra and take it to sister algebra. Usually such a naive approach fails, usually. But my experience tells that when I can take care of K-theory very well, then sometimes such an idea can not be very useful. This is, I'm talking on such topic. So, right. So, throughout my talk, it's either this group. And A the sister algebra is a unitary. The only thing I assume at the beginning is that there's a natural map from the quotient of the unitary by its connected component of identity. Then assume that this is one. And there is the Kirchberg algebra. So at the end, I concentrate on the Kirchberg algebra. So this is something too. So and so I start with cocycle. It's a pair of alpha and mu. This is a cocycle action Z on A. So it means that so alpha is a map. It's not quite an action. It's almost. So it's a map from Z into the automorphism group. And U is a two cocycle, so it's U is a map from Z cross D to the unitary group of A, satisfying situation. This is not quite alpha Z8, but you have inner part of it. Okay? And so this inner part, so it's a unitary satisfied two cocycle relation. Such a pair is called the cocycle action of G of A. And then if you're given a cocycle action, you need to take cross product. So it's very nice. Right. And then and for if you're given two cocycle actions, then there is a natural notion of equivalence. Or you say that two cocycle parts are common. There is a natural notion, but since I don't use the complete formula, so I don't explain. So then I want to raise the following question. Maybe I should write this. Question 1. Assume we are given a cocycle action. Then, how one can tell? So this is the equivalent to a genuine action. So when you use identity, constantly identity, then we say that it is a genuine action. So how one tell? How can one tell this is equivalent to action, an action? So I want to do For fundamental algebras, usually this is a relatively easy question from so A is a factor, properly empty factor, then it is always equivalent to genuine action. And when the group is finite, it needs to as well. But for sister algebras, then there are a lot of obstructions. And the first obstruction you can think is a very easy thing. So I want to keep this question. So since we have unitary, bunch of unitaries, so we take this K1 plus. Then it turned out to be, well, of course, then this satisfies the two cocycle relations. From this, you get a cohomology class. Second cohomology with coefficient in K1. So if this class survives, then there is no way to perturb these two genuine. So it's an obvious. Suppose this is supposed to be an obvious obstruction. So assume this obstruction vanishes. Then, by perturbing the given cocycle action, then we may assume. So this belongs to the connected component of the unitary group of A. Although this perturbation is not canonical, so it's the best subtle thing. Anyway, so we assume that this is in the connected component, so we can find a path from identity to this unit. A path, continuous path. From identity to unitary. Then we consider the following class. The foreign function here should be minus. Right, so when t is 1, no, when t is 0, then of course by definition it is identity. But when t is 1, again, thanks to the two cocycle relation, so again you get identity. So this way you get a closed loop. And so it is in Q1. Of the suspension domain. Let's call this C prime G. Okay. Then it turned out that this satisfies the three cocycle relation. So from this you get a side of G. Right. G with coefficient in, so it's a K1 and the suspension it's K0. So again, this class is no obstruction. So the natural question is when this class vanishes, then what can you? Actually, this naive approach, so I cannot really continue this naive approach. So when the dimension is larger than or equal to 4, then I cannot really continue this. But today I want to explain something better. And for that, up to here, so you get just a algebraic cycle, but you need to continue this, then you need a nice topological interpretation of these things.
You mean higher cohomology? H4 or something?
Yeah, I want to define H4 when this class vanishes, but this naive approach doesn't. Right. So this is the first program. First question I want to talk about, and the next next question is about one cocycle, one or group action. So assume now, so you are given a group action. So this is honest. Then, okay. A family of unitaries in the unitary group of A. So is an alpha cocycle. If you have one cocycle relation. So, and you might ask why you take care. So you stick to these things like a two cocycle action. You don't really need to care two cocycle, one cocycle. But actually, so when you work on only group actions and not cocycle action, and you want to classify these actions, then eventually you have to work on two cocycle actions and also one cocycle problem, as in your thesis. So typically you go to neutral product and you have to show second component balancing, first component balancing, and so on. And I also take that strategy, so we care about these problems. Now, so we want to with a similar question. So alpha action. And the one with the alpha is the one cocycle. Alpha cocycle. And we ask similar question. So how one can tell this one cocycle is a coboundary. But since we are generally working on an infinite group, so this is not really a good question because it's quite rare that a given one cocycle is an exact coboundary. And instead, we need an approximation version. So we need a word here, asymptotic. So we ask, how can one tell that a given one cocycle is an asymptotic coboundary, meaning that whether there is a continuous family of unitaries, say in connected component, such that so this converges to this. The second problem I want to talk about today. And again, so in a similar way, we can find obstruction. And well, the story is pretty much the same. So also, the first thing you can think of is K1 class obviously. So this gives you a common class only. Then, okay, so this is clearly obstruction. So assume before this class vanishes. Then we may assume that Z belongs to the connected component of the identity. Now we do the same. We choose a path. We choose a path, continuous path. from identity to UZ. And this time what we do is the following. So we define gamma G. So perturbation of V and define WHC this way. Then it has turned out that this pair is a cocycle. On the suspension node. So starting from one cocycle problem, you get a cocycle action. Naturally, you get cocycle action. So using the story I already told, then from here, so you get H2 obstruction. Okay, what is substantial A? So this is K north of A. And again, if this class vanishes, then we will get a sort of
When you end up in K0A, that's basically predictions. There must be some other way, some way to see these predictions in matrix algebras.
That's right. Yes. Actually, projection will appear in my program. Not in this context, but in the case of cycle action. So these two questions are very much related. But well, this again, this approach stops at 3. Right. So now I want to talk about the third question. Actually, that's the main subject. And actually, that's a problem I originally I was working on with Hiroki Matui. So it turned out that this question should be solved for solving the main question. So from now on, I assume that A is a Kirchberg, so it's really a nice stuff. So, but you don't really need a definition. Let's, for example, so you can take A, Kunshan's real length. This is a typical example of algebra. So you can think of it. Right. So we consider two group actions. These are honest actions. And we want to classify them, but for the classification, then we need to use a right notion of an equivalence relation. And in my opinion, the following equivalence relation in this context is the most useful. So I assume that alpha and beta are, it has a terrible name. Take it to reveal cocycle. Cocycle conjugate. If so, there exists an alpha cocycle. And gamma, it is an automorphism. With the KK class is the same as the KK class of identity. Such that the cocycle perturbation of alpha is conjugate to beta by this gamma. get a cocycle conjugate with special gamma. Right. So our goal is to classify reasonable actions of reasonable group in P up to cocycle conjugates in this special sense. So, okay. So, question 3. So, we are given two actions. And how? Okay. Alpha and beta are equivalent in the above sense. Of course, in terms of certain invariants.
Can you explain why the KK of gamma should be KK of the identity?
Because if you use a gamma which has a non-trivial KK invariant, then it destroys the invariant of it. It changes the invariant. I don't want the gamma change the invariant of it.
Do you have a method how to compute KK theory of this gamma? Because, for example, A can be quite bad algebra, like, of course, if it's Kuhn's algebra, maybe there are methods, but there are this kind of...
Yeah, but the A is a Kirchberg algebra, so in principle.
Yeah, but in
KK
principle,
theory is
for
understandable.
example, there are those algebras, Kirchberg algebras, which come from actions of groups on
Yeah, but when the
buildings.
K groups are finitely generated, then it's pretty.
Yeah, but I mean, there is no way to compute them. That's why I'm just interested
Oh,
how you
okay,
would
so
compute KK, right?
It depends on the level of the program you are thinking of course.
No, like to find the actual group.
Yeah.
So there is no kind of
But
intrinsic
I often
method.
concentrate on the Kuhn's or anyway. So, but again, so you can find the immediate necessary condition. So assume our data rerun. And this immediately implies that the KK class of alpha G and beta G are the same. This is an obvious necessary condition. And moreover, so the reason why I assume that the Kirchberg algebra is the following. For such gamma, then, so there exists a continuous family of unitaries. Such that, so gamma is continuously approximated by the inner automorphism given by Pretty. This is the reason why I work on Kirchberg algebra. So then, in this special case, so using this relation, you can see that the G is the limit of the following. Inverse UG alpha G. And you should notice that this part, for each t, this part is an alpha cocycle. So it means that the beta g can be approximated by a cocycle perturbation of alpha g, and the cocycles should be taken continuously. Right? So this is a necessary condition. This part is the alpha cocycle. So this is a rather obvious necessary condition. So I want to talk about the obstruction of the existence of such a continuous family of one cocycle. And for that, then I need to introduce some notation. So in the case of fundamental algebras, and when you want to classify group fraction, then there's no way to avoid using the root of product and the central sequence algebras. And we need something similar. But actually, the sequences are not enough for system algebras. We need continuous function. So I use this notation for the asymptotic algebra. This is the counterpart of the root of product. And I often work straight. So in the system algebra, then there's a continuous function. So A is a subalgebra, system subalgebra of this asymptotic algebra. Then quite often I need to work on this. So this relative combination makes sense, right? Since A is a subalgebra of this asymptotic algebra. So this is the counterpart of the central sequence algebra in forming algebra complex. Right. So let's see. There is no obstruction for the existence of continuous family of alpha cycles approximately there. So assume you're given two actions. And I assume the first necessary condition. So we assume only this, and we see such a continuous family of one cycles. Then what we do is that we choose for each G continuous family of unitary. That, well, we can do it by using Kirchberg Phillips theorem, then we can do this. This converted. But since this is an arbitrary choice, so there isn't, you cannot really assume that the alpha T form a one cycle. So let's compute the failure of a one cycle relation. This is the failure of a one cycle relation. And then this belongs to the asymptotic centralizer because of group associativity of this action. Then we define D by the perturbation of C by this family. But this automorphism is regarded as an automorphism of this asymptotic center. Then this way you get a cocycle action. Of G on this terrible monster. Then at least from here, so you can get so you go back to the question one. Oh wait, I have to say that it turns out that so this two cocycle action is equivalent to a genuine action if and only if. So you T can be chosen. To form one cocycle, alpha cocycle. In the asymptotic algebra, not pointwise, but it's good here. So clearly, this is a necessary condition for alpha equivalent, for alpha and beta equivalent. So then for that, then we need that this two cocycle action is equivalent to the genuine action. And going back to the question 1, and from here you get so H2 obstruction with coefficient K1 of the asymptotic centroider. And if this vanishes, then you can go on K0 of this one. It's other homology with coefficient. But you might wonder, this is an inseparable huge system algebra, so you may wonder whether you can compute the K theory of this or not. But in fact, you can compute it. And it turns out that they are very nice. They're very nice groups. Anyway, so this is not Masaki Izumi, it's Matui and Izumi. So, K groups of this asymptotic centroider is canonically isomorphic to KK of A. So it's computable. Well, maybe it's not computable for you, but at least it's isomorphic to a very nice group. So these invariants are used. But as I told you, they have to, well, this is nice up to dimension 3, but if you go beyond that, then you have to do something else. And I'm going to talk about it.
Sorry, does one see on the left-hand side the product?
Product. Yeah, I think so.
What's the
Because if you are given two projections, and you take naive product, then it's not a projection. But since this is an asymptotic centroid, so you reparameterize one of the projections, then you get a projection, almost a projection. That's the thing.
yes.
Actually, if you're given a projection of this algebra, then what you do is that you want to construct an asymptotic morphism.
Yeah, exactly.
So if you're given PT, then you consider map X sending PTX.
Yeah.
Since P belongs to the asymptotic centroid, that way you get an asymptotic morphism. Right. I want to go to the answers section. So from now on, so I assume that this horizontal group in the sense that G has subnormal series. That Gi plus 1 is isomorphic to Gi semi-dark graph with Z. So this is a project. A typical example is Zn, but also it includes a co-compact lattice of two connected solvable Lie groups. So Heisenberg group is one of the examples. So I concentrate on this class of groups. And this number n, so this number n is very important. this is called a huge length of
So GN is G.
yes. Sorry, I should write this. Yeah. So this is so-called huge length. And this coincides with the cohomological dimension. So actually, so this number doesn't depend on the particular choice of subnormal sequence. Subnormality. Alright. First. So in the above situation, so Z is for Z, A is Kirchberg algebra, alpha and beta. Alpha and beta alpha. Then alpha is equivalent to beta. You can only actually so there exists a continuous family of unitaries in this graph and one cocycle relation holds in asymptotic algebra, not pointwise. So actually, so this is necessary sufficient condition for alpha and beta to be equivalent. And the proof of this requires a lot of analysis using Lorentz properties. So H2 stability, H1 stability, and so on. So H2 stability means that if you're given two cocycle action whose cocycle is very close to one, then it is coboundary. That's H2 stability, and H1 stability is that if you're given one cocycle which is very close to one, then the cocycle is asymptotic coboundary. So you have to produce a lot of these results by using analysis, Lorentz properties.
Plus some classification program things from Kirchberg. Yeah.
Of course. So now, so since this is a necessary and sufficient condition for equivalence, so we want to deduce invariant forms, algebraic or topological invariant for this happens. So here I have to introduce one more term from an algebraic topology. So assume X is a topological space and it is a G space. So X is a topological space on which G acts continuously. Then we want to consider the following. And G equivalent map. G equivalent map from the universal covering of the classifying space to X. We consider such a map, and this is called homotopy fixed point. And I learned this word from Andre Enriquez during the workshop, second workshop. So this comes from this program. Though I already considered such map, but I didn't know the right name. And this turned out to be very useful for our programs. Because you get the answer from first and second question in terms of the subject. And in fact, so if you are given such a map, then well, actually, if you are given zip space, then you can consider fiber boundary, say E, divided by a diagonal action. Then you project onto the first component. Then you get a fiber boundary on the class over the class one space. Then it turns out that there is a one-to-one correspondence between F, homotopy fixed point, and the section of P, continuous section of P. Right. But for the existence of a continuous section, then there is a classical theory, obstruction theory, giving you a lot of combinating class. So now I start with the answer to the second question. So assume we are given the action, okay, on the Kirchberg algebra and the cocycle, alpha cocycle. Then we can, okay, we can consider the following action. So this is an action as just a topological space, not as a group. So the unitary group of A is topological. But for simplicity, I assume this. Then it's clear that okay, this action has a fixed point if and only if UG is a coboundary. Right? This is V if and only if UG is a coboundary. So it's important to see whether this has a fixed point or not. But as I told you, so when G is infinite group, then it's quite rare that you get a you can make a given one cocycle into a coboundary. So we need an asymptotic coboundary. And it turns out that right. This action is the action on the connected component of the unitary group, right? The homotopy fixed point. If and only actually the like this continuous map satisfying this relation. So if and only UG is asymptotic coboundary. So this is the precise answer first and second question. And as I told you, the existence of such a map is the same as the existence of a continuous section for certain fiber band. And it turned out that the cohomology class I talked about can be identified with the classical obstruction class of fiber band. So you can go on beyond dimension 3.
So but where's the bundle? I don't see any X in it.
X is a
How do you get it?
X is a classified space. So when okay, group is at the end, then it's an n torus. Yes. So this is the first answer. The answer. This is the answer to the second question, and for the first question, then you need projection. 1. So you're given one cocycle action. Okay, you're given cocycle action and you want to see if it is equivalent to a generic action. So starting from cocycle action, you take cross product, then you can consider the dual action, then again you take the dual action, so you get a second dual action. Probably the second dual action is a bit confusing. The dual action of the dual action. Then even if you start with cocycle action, you get a generic action. So there is some misery. This is the dual of dual. On this stable system algebra. Right. So here, let's consider this. This is a set of projections. Such that the class is equivalent to the class of unit of A. Assume A is the unit of A. So consider this space. Then since alpha G preserves the identity of A, so this action preserves this space. So you get a G action on a topological space. And the cell is there. Okay. This again, this action. The homotopy fixed point. If an anomaly, so this given action is equivalent to an action. So this is the answer. Again, so you can compute the homotopy groups of this space, and then the cohomology class I told before can be identified with the usual obstruction class of fiber boundary. But these answers are tools for main problem. It's a classification of group action. It's not quite finished. But we've just finished the answers of these two questions, so we are now working on the program. So we have a conjugate. So given, okay, alpha, this is an action. Then we consider the following principal boundary. So this is so this is a principal or asymptotic boundary. And here the action is that it's a left translation. So this is a dual. this way you get a principal order A tensor K bundle. And so our conjecture is that assume alpha and beta are after, then these two principal bundles are isomorphic as principal bundle. Strictly speaking, so this isomorphism should be best point preserving. If and only if they are equivalent. And actually, the conjecture is true for up to. So this is true. If then is at most 3. Actually, about 5 years ago, I got this result. We got this result, and we stopped there. And Matui was busy in working on something else. I was busy in classification of subfactors. Recently, we came back to this program and to attack a group with higher huge lengths. Then we realized that we need to solve these 2 questions. So we just solved these 2 questions. So now we attack this conjecture. So it means that well, group action. So pointed group action pre-delete groups with huge lengths less than equal to 3. Then we can classify this group action on Kirchberg algebras. And for example, so for an A, when the huge length is 3, then there is a one correspondence between the alpha actions of Z on N and the second cohomology. So this is a complete classification. And here, the third confluence doesn't appear, and this that's because of just the position of identity. And if I go to Morita equivalent systems, are not isomorphic A, and then now I need a third cohomology. It's very subtle. Classification really very subtle.
I mean, is that result true for finite groups?
For finite, it's very difficult.
Very difficult.
Because well, an intuitive explanation is that the cohomological dimension is infinite.
Is that,
So it's infinite dimensional object.
but it could be true for other reasons. I
Yeah, it
mean, in another sense, finite groups are easy, right? The analysis part,
yeah, but
sort of cohomology.
sister algebra is
Right.
non-commutative. So at the end of my talk, I want to mention the relationship between this work and the Pfennig generalized explainability theory. So when you see this conjecture, so you may wonder whether this is this is easy to verify. And in my opinion, the left-hand side is much easier problem. The reason is the following. Actually, so if this conjecture is true, then the problem is reduced to a purely homotopy theory. And so let me show one reason that I make that statement. So that was okay. So the information this principal boundary has is the same. Basically, is the same as the information for the associated bundles. We have principal bundle, so we can consider associated bundle. So this is a continuous field of sister algebra, and this is section sister algebra. So this is so-called generalized mapping terms. So this is a continuous field of sister algebra with fiber is A tensor K compact, and the base space is a classifying space also. So, but this thing, so this continuous field is not as bad as you think. Actually, so data of X. They show that. So if D is strongly self-absorbing, so just think of O infinity. It's out of O infinity. So forget about the function. Just think of it's out of O infinity. And you consider the set of okay. So X is a compact metric space. When you consider a set of continuous fields of sister algebras over X with fiber, you can say compact. And then show that this is a generalized homology set. So it has a group structure. So this is the equivalence class of conjugate. And group operation is given by tensor product over C of X. So this is a generalized homology set. And you have a spectral sequence to compute this. Right, so question. So dynamical realization. So when these say strongly self-absorbing fields are out, and you cut E by projection, with the class is 0. Okay. Then from the group actions, you get a generalized mapping to us. So it is a continuous field of sister algebra. So isomorphism class of this field exhausts all of them. That's a question. When X is B, EG. So we can think of this dynamical characterization first. And first now it says that find these for Z and whose value is less than or equal to 3, then it's 2. Affirmative. So our classification theorem says
Can you just pull down?
so I think our time is over.
Questions or comments for the speaker?
say something.
Well, once you get a, that's okay. So in the case of Kunz algebra of N and huge length less than 3, then I think it's the same as the cocycle conjugate. Because well, on N, then every automorphism is approximately infinite. And well, one cohomological, I mean, actually, so it's, I think it's just by coincidence. The situation too simple in that case. In general, it's probably difficult to compute by.
So in the von Neumann case, there was a problem with flows, and that when you went to the alpha product, it was not continuous. You lost continuity.
Right, right.
But you probably still have continuity.
You have the same problem.
They have the same problem.
You have the same problem. Or continuous groups.
So there's no hope for doing flows.
Any more questions or comments? Before you thank the speaker again, I just want to remind you that there's a beer and pizza after this talk back in the main building. The food should arrive in half an hour or so. There's beer, so you can start out with that. Anyway, thank the speaker again.